In this tutorial, we are going to talk about simulating the mechanism of a welding robotic arm in SimLab Composer. This is a section of a production line and it has a robotic arm and two products on a conveyor belt. The robot arm's main function will be to weld the top surface of the products. Let us begin by creating a path which will be used as a guide for the arm's movement. From the Create menu, select Paths, then Composite. Set the creation type to be in 3D space and click OK. Switch the type of the composite path to a B-spline path, which is smoother and can contain curves in its build. The first point in the path will determine the robotic arm's first point of movement, so click on the tip of the welding tip to create it. Now begin placing points on the welding target to create the path where the robotic arm will perform its task. Make sure that the path's last point is near the path's first point to restore the robotic arm to its initial position after going through the path. You can click on the hard points of the path and adjust their position to control the shape of the path. Once you are satisfied with the shape of its path, click on the green mark to finish the creation process. Select the path and move it upward slightly, since we do not want the tip of the welding arm to touch the surface of the product, but rather have some space between them. Click on the workbench icon and select Simulation. The solid creation window will appear. From this window, you can select which components to convert to solids. Converting an object to a solid turns it into a simulation-ready object. The Auto Detect Solids option will automatically convert all the components to solids based on their structure, but since we are only interested in simulating the robotic arm with the other elements in the scene, select the components of the robotic arm and click on the Multiple Solid Creation. Click on End Solid Creation to proceed to the next step. As you can see, hovering over the robotic arm's components with the pointer will highlight them in red, indicating that they have been converted to solids and are ready to be simulated. Now we need to start adding joints to define the interaction between the robotic arm's components. Before we start adding joints, click on the base of the robotic arm, then click on the lock icon in the Solid Properties panel. Locking a solid will restrain it, and since the base of the robotic arm is fixed into the ground, it will be restrained and not move along with the arm. Click on the Links menu and select Revolute Joint. The Revolute joint creates a relation between the two solids where they are only allowed to rotate around a single defined axis. Click on the base of the arm to set it as a solid one, then click on the component attached to it to set it as solid 2. Then click on one of the component's rounded loops to define the location of the joint and the axis of rotation. Now that the solids are connected to each other and the axis of rotation has been defined, toggle on the Impose Joint Limit options. Limiting the joint's range of rotation gives you control over the behavior of the robotic arm, and depending on the position of the robot's target in relation to its own position, you can determine those values while keeping in consideration the reach point of the robotic arm. Set the range for this joint to a value of -50 to 50. Create another revolute joint and connect the following two solids in order. Set the axis of rotation for this joint and limit the angle of rotation to a value between -130 and 130, since we need this joint to extend and reach the far side of the product. Add revolute joints to connect all of the remaining solids with each other in respect to the arrangement of their structure. Now that we have connected all of the robotic arm's components with each other, we need to link the arm to the path we created earlier. From the Links menu, click on Path. Set Solid 1 to be the welding tip of the arm, and Solid 2 to be the ground, since the path we created is stationary and is not attached to another solid. Then select the follower point by clicking on the tip of the solid to define precisely which of the solid needs to be following the path. Now click on the path you have created to set it as the path that needs to be followed. The last step is to enable the trajectory motion option in the path link. The trajectory motion is the force that will be driving the robotic arm along the path. Select the motion function that you want to use along with its value and click OK. From the Simulation menu, click Start to begin the simulation process. Once the simulation has ended, click on the Workbench icon and switch to the Animation Workbench. A message will appear asking you whether you need to save the simulation you have just created as an animation. Click Yes. Set the frame's conversion rate to determine how smooth the animation should be. Usually a value of 30 is recommended for the conversion. The simulation we have created earlier is now baked on frames over time as an animation and can be incorporated in building the scene. Extend the maximum number of frames in the timeline by setting it to a value of around 650. Select all the keyframes that have been created by dragging a marquee box around them. Then press Ctrl and C, then Ctrl and V on your keyboard to duplicate them. Select the duplicate keyframes and drag them to the right in the timeline. Copying all of the baked keyframes and sliding them to the right will create a loop in the animation, which we can use to mimic the repetition in the robotic arm's task. Set the timeline slider to the first frame of the second animation. Then select the two objects on the conveyor belt and move them along the x-axis as if they were driven by the belt, and try to match the second object's location with the created path. Play the animation to see the result. SimLab Composer's Simulation Workbench allows you to simulate sophisticated movement patterns easily. Powered by advanced mathematical calculations embedded in the simulation engine, analyzing and understanding advanced mechanisms has been an enjoyable process. In combination with the ability to convert the simulation into an animation, sharing your simulation as a 3D PDF or as a rendered animation sequence is no longer an impractical choice.